So we're now thinking of psi tx as the probability density function of what's now is going to be called the Brownian motion at time t. It is the limit as delta t and delta x went to 0 of this scaled interpolated random walk. And of course the probability density is nothing other than the derivative of the cumulative distribution, or said in another way, if you want to compute the probability that the Brownian motion stays, say, to the left of the level x, say I put my level x here, the probability that by time t the Brownian motion is to the left of this, it would be computed as the integral, all the way up to x against the density, right, integrating over this variable, free variable y. So, it would sort of be like asking the question, what's the probability that, in time t, this blue dot, the Brownian particle, stays to the left, left side of the, the edge of that box there. And that would be the kind of how you would do that calculation. And, we already saw that this psi t, the probability density function, solves this partial differential equation here. And if you take a course on PDEs, you'll kind of learn how to solve it. Here, I'll just tell you what the solution is. It's given by this. This is we recognize this hopefully as the probability density of the normal random variable with variance sigma squared t. So hopefully this is looking familiar to you. If not, you want to review normally distributed random variables. And this PDE again is in this form. The solution to it is the same as they appear in Einstein's 1905 paper. You can take a look, and if you want to solve this PDE, you'll have to what's called impose an initial condition. So this by itself has infinitely many solutions. You want to kind of say what was the probability density at time 0. In other words, we want to specify psi of 0 at every point x, and that's kind of like asking the question, what is the probability density of the Brownian motion at time 0? Well, the Brownian motion at time 0 was just 0. It's a process that always starts in 0, and that's by convention, and you're kind of, unless told otherwise, this is what you're always going to assume. You can see why this was our Brownian motion approximating process. And if you take t equals 0 here, nothing remains in the sum, and so we start at 0. It's not surprising why the Brownian motion starts at 0. So the question is, what is the probability density function of 0? It's maybe a strange question, but you can kind of formally write it as so. This delta 0 function looks kind of curious. It's called the Dirac delta function after yet another physicist, Paul Dirac. It takes the value infinity at 0, and it's 0 everywhere else. So this is sort of what it looks like. It's 0 everywhere on the real numbers, and at time 0 there is what's called an infinite point mass. So if I could draw it, I just left it as an arrow. So there's sort of an infinity value placed at the point 0, and that is kind of one way of specifying a probability density function of a constant number. So why is it a probability density function? Well, by convention, one assumes that the integral of this thing, to try to think about integrating this function, what would it be? Well, the convention that kind of mathematicians take is that the integral over an infinite point mass is going to be, just integrates out to 1. So it's 0 everywhere, and you pick up 1 point mass at 0, and so therefore this Dirac delta function is kind of now by definition a probability density function, and clearly it's telling us that the process must start at 0 because the probability density is 0 everywhere else. Only at the origin do we have any probability mass, and that's kind of what it is. You can also try to verify the answer in the following way. So first of all, you should kind of run the following calculation. Make sure that this actually satisfies the PDE. How do you do that? Well, you take a derivative with respect to time, set that equal to the left-hand side, and now take two derivatives with respect to x, and hopefully verify this equation. And then you should also be able to verify this initial condition here, try to take, t down to 0 and see if you can get infinity at the origin and have it be 0 otherwise. So, that would just involve taking x to be, kind of different values, take it to be 0, right? And if you do that, what happens? Well, then this term goes away, and you take t down to 0, this blows up to infinity as asked. And if this is not 0, if it's any other value but 0, this is going to be a positive number. So now when you take t down to 0, this exponential term will decay faster than this inverse term, bringing the answer down to 0. So you can try kind of a practice working those calculations. And yeah, in general, if we're looking to compute an expectation of the Brownian motion, or rather some function of the Brownian motion at at time t, then what do? Well, you just integrate it against the density. So g of x integrated against the density over the entire real line will give you this expectation. And so something you have in the homework, in the options problem, this would be the function g, and this is how you would evaluate this expectation. And then finally, this is kind of a visual representation for what the density looks like. This is another possible path of the Brownian motion, and here it is, potentially, at time t. And if you want to compute the probability that it's below x, so if let's say I place the value x here, right, the integral of this density, this is our bell curve, the normal distribution, the area, the shaded area, if I were to shade this, area, would be that probability mass would correspond to this probability. And you kind of you see what it looks like. Hopefully you kind of recognize this as the normal distribution, and here is the standard deviation. And so this is how much where you expect the Brownian motion to end up after t time units. You expect it to be within this bandwidth of the origin. So it's this is the standard deviation is just the square root of the variance, so it's sigma times the square root of t. So you expect, kind of on average, the Brownian motion to sort of be, first of all, at 0 and within, one standard deviation. And so you can see as time goes on, the Brownian motion becomes kind of highly erratic, and, the standard deviation grows as the square root of t, and you sort of can find it, pretty far away from, from the origin. So, we kind of, with respect to this movie example, again, you sort of, after a while, you expect it to leave the box. Simply because the standard deviation after some time becomes very, very large, and the Brownian motion will can get away from the origin. The final thing I want to mention is the connection to the central limit theorem, which is maybe a more modern way of developing the Brownian motion as a process. So let me just mention this so you're aware of that type of approach. So hopefully you remember the central limit theorem. This is from Ross. It just comes down to taking a bunch of identically distributed random variables, as as said there, and when you form their sum and scale it by the square root of the number of summons and divide it by the standard deviation and subtract off the mean, that ratio there will tend towards the normal distribution. So let's look at sort of, how do we apply it to our case? Well, this would be the CLT applied to these summons here. These are the xj's. What is their mean? Their mean is 0. Remember, these were plus or minus 1 with probability 1/2. So the mean of that random variable is 0. And what were their variances? Well, the variances were 1. Again, they're just take the values plus and minus 1 and compute the variance of that random variable, and it's equally likely to be plus or minus 1. The variance is just 1, and that's what that sigma is. So that sigma is not to be confused with this sigma here. The sigma is this one, the sigma of the increment of the random walk. And that's exactly what what I've written here. This is my I missed the square root. So I do need a square root. This value here is just representing my square root of n. Notice there are n things in the sum, and this is how many things I have in the sum. And this is, it's telling me that that's indeed the case. That's how many things I have in the sum. delta t is what went to 0 here, which is the same thing as saying n goes to infinity in this way of writing it. And on the right hand side, what you have is the normal distribution, and in our case it has mean 0 and variance 1. So I guess I can mention kind of one more thing, which is I guess towards the bottom here. How do I get to the fact that the distribution of the Brownian motion at time t is actually normal with variance sigma squared t? Well, this one, if this random variable converges to normal with variance 1, what happens to this, to this thing? This is the scaled random walk that approximates the Brownian motion as delta t and delta x go to 0. So we kind of see how to deal with this term, but then this delta x, kind of maybe, messes things up for us. So, what happens if I just take this guy here, substitute this term, and then multiply by, delta x times the square root of t over delta. So this would cancel out that, leaving me with a delta x. And notice that this product here converges to the square root of sigma squared t. What happens when I take this and multiply by a normal variable variance 1? You get a normal random variable with variance sigma squared over t. Right, so that's a property of the normal distribution. If you take a normally distributed random variable and you multiply it by some number, say this one, call this number a, then the random variable that you obtain, namely a times this normal, is going to be normally distributed with variance a squared. And so, this is going to be the standard deviation, and you square it to get the variance, which is exactly what we had in the probability distribution there. So hopefully you can see, how this process comes about, and we, get to see its most important property, the normally distributed property, and then I'll wrap up this, lecture with some connections to the Poisson process and, how one defines the Brownian motion, maybe besides just mentioning this partial differential equation and just this density.